Hi, I'm Eddie. I'd like to show you how to solve the coding question, shortest path in a grid with obstacle elimination. So first, in this video, I'm going to give you a visual explanation of the algorithm. And then in the next video, I'm going to live code it while explaining it so that you can see a demonstration of how you would live code this during an interview. Okay, so here's the problem that you're wanting to solve. Let's say you have a grid and there's a start position and there's also the goal, your destination you want to reach. And there's also some walls. So in this case, this obstacle is this red block right here. So the goal is to find the shortest path from the start to the goal while avoiding the walls. So you can step in any grid location that's not a wall. And you can eliminate k obstacles where, for example, k might be 2. It's just whatever the gets input into the function. So let's first ignore this second part of the problem and just figure out how we find the shortest path while avoiding walls. So if we have a start position at row 0, column 0, it takes 0 steps to get there because we start there. And if we move to row 0, column 1, it takes 1 additional step. We move to row 1, column 1, it takes another step, so there's 2 steps total so far. Then row 2, column 1, that's 3 steps. And then row 2, column 0, that's 4 steps. And then we've actually reached the goal. Okay, now let's think again about what happens if we can eliminate k obstacles, at most k obstacles, where, for instance, k might be 2. So we start again at the top left corner, and as before, it just takes 0 steps. And then we can break through a wall. So we have that option. So we used one wall breaker, and now it takes 1 step to get to this position, and then it takes another step to get to the goal. So it only takes 2 steps if we're allowed to break through, eliminate certain obstacles. Alright, so let's first solve a simpler problem before we get into figuring out how we solve this full problem. So the simpler problem is just ignoring that second statement. So we just look for the shortest path while avoiding walls, and we don't think about how we can eliminate obstacles just yet. So how do we do that? And by the way, if you're familiar with shortest path, then please go ahead and skip to later on in this video where I'll show you how you do handle eliminating k obstacles. But if you'd like a refresher, then please go ahead and watch. So we can use breadth first search. And when we do that, we use a queue. So queue takes items in a first in, first out basis. So this is kind of like when you're waiting in line at a grocery store to check out your items. The first person in the line is the first person to reach the cashier and to be able to check out and buy their items. So we also want to store inside the queue, each item will store the state. And the state in this case is the row number and the column number. So it's saying which position in the grid you're located in. And you also want to store the number of steps it took to go from the start position to this particular row and column state. And finally, you're going to have a set of visited states, which is all the states that you've already visited because you don't want to backtrack and revisit someplace that you've already seen. Okay, so we start at row 0, column 0. We put that onto the queue, and we also store the number of steps, which is 0. So that's how we initialize our queue. And then what we'll do is we're going to pop that first item off the queue, and we're going to look at that as the current state and the current number of steps. And so at that current state, what are we going to do? We're going to check its neighbors above, below, so up, down, and left, right, and any neighbor that's valid, we're going to add it to the queue. So in this case, we can't go up or left because it's falling off the grid, and we can't go down because there's an obstacle there, and at this point we're ignoring that statement that we can eliminate k obstacles. So we can move to the right. And so the right is row 0, column 1, and it takes 1 step to get there from the start position, so the number of steps is 1. And we're going to add that to the queue. So row 0, column 1, and 1 step. And now we're going to store that 0, 0 state into the visited states because we want to make sure we're not backtracking in our search. And we're just going to remove the number of steps. Just keep in mind here that in the visited states, you want to just save the state, the row number and column number, and not the number of steps. And that's because if you did accidentally store the steps in the visited states, what ends up happening is you end up revisiting the same state, the same row column, when you have a different number of steps. Okay? So don't worry too much about it, but just remember that the visited states just stores the row and column and not the steps. Okay, so again, we'll pop off the first item from the queue. So the row 0, column 1, and also the number of steps. And we'll again search the neighbors. Up, you can't go up. You can go down. You can't go left because you've already visited that state, so you don't want to go backwards. You can't go right because that would fall off the grid. So when you go down, then that's row 1, column 1, and that takes 2 steps. So it's one more step from that top right corner. So it's 2 steps from the start state. You can put that on the queue, and then the current state, you want to save it in visited states so that you're not going to backtrack, and then just get rid of that number of steps there. Okay. So again, we're going to pop this first item off the queue, and then for row 1, column 1, again, visit the neighbors up, down, left, right, and the only place we can go is down. So we're going to visit row 2, column 1, and that takes 3 steps to get there. We're going to put that on the queue. Okay. And then again, we're going to store that state in the visited state and get rid of the steps. So we'll pop off the queue. That's row 2, column 1, and 3 steps. Visit neighbors. We don't want to go up because we've already visited 1, 1. We can't go down because that falls off the grid. We can go left. We can't go right because it falls off the grid. So when we go left, that's going to be row 2, column 0, and it takes 4 steps to get there because 3 plus 1 is 4. So we're going to put that on the queue, and again, store the visited states. Now we pop off from the front of the queue, so row 2, column 0, and here's when we notice that we've reached the goal, and so we can return the number of steps, which is 4. Okay, so this is the basic version of shortest path that you may have seen before in other classes or studied before. So now, let's see how we can modify this to handle obstacle elimination. So here we have this same layout again, but we're going to modify it so we can eliminate k obstacles, and as an example, let's say k equals 2. So what we can do is we can update the state so it's not just the row and column, but also the number of eliminations remaining. You can think of these as hammers that you can use to break down the walls, and once you use one hammer to break down one wall, you can't reuse it. So if you started with 2 hammers, you break down 2 walls, then you end up with no more hammers. Okay? So for example, if you're in the top left corner, you're in row 0, column 0, and you're also in the state with 2 eliminations remaining, meaning you have 2 hammers that you can use at any point to break down 2 walls. Okay, so here's the state row column elimination, and we're going to go 0, row 0, column 0, and 2 eliminations, and that starts with 0 steps. We're going to initialize the queue with that item, and then we're going to pop it off the front of the queue so we can look at it. And what we do here, we're going to look for the neighbors that are valid. We can't go up because it falls off the grid. Now we can actually go down because we're allowed to break a wall. So let's break that wall, and we used 1 wall breaker. So now it's row 1, column 0, and we have 1 elimination remaining because 2 minus the 1 that we used is equal to 1. Okay, and that takes 1 step. So let's put it on the queue, 1, 0, 1, and 1 step. Okay, so we can't go left, and we can actually go right. So it's row 0, column 1, 2 eliminations, and that's 1 step. So we'll add that on the queue as well. Okay, so now let's put that in the visited states. So the visited states now includes the state that has 3 values per state. It's the row and the column and the number of eliminations. And again, we're not storing the steps in the visited states. Okay, so now let's pop off the front of the queue. Let's first also shift everything to the front of the queue now. Okay, so now let's look at the neighbors for the state 101. Okay, so we don't want to go up because we've already visited 002. We can go down, so that would be row 2, column 0, and 1 elimination remaining, and that takes 2 steps. So let's put that on the queue. We don't want to go left because it'll fall off the grid, and we can go right, so that's row 1, column 1, and 1 elimination. That takes 2 steps to get there. Okay. Alright, so now we're done with that. We're going to store that state in the visited states and get rid of the steps, and then pop off the front of the queue again, and then also shift all the other items forward in the queue. Okay. So now for row 0, column 1, 2 eliminations, that's the top right corner. We don't want to go up because it falls off the grid. When we go down, here's what's interesting is that we're actually going to store a different state. It's row 1 and column 1, as we've seen before, but this has 2 eliminations remaining because we didn't use it when we went from the top right corner. We didn't need to use any obstacle eliminations, so we still have 2 remaining. So it takes 2 steps to get there. So we don't want to go left because we've already visited 002, and we don't want to go right because it would fall off the grid. And so the key point here is when you look at these 2, 111 and 112, these are 2 distinct states. Even though you're in the same row and column, they're different states because you have a different number of eliminations remaining. Okay? So we want to store that on the queue as well. 112 takes 2 steps to get there. Okay. And again, let's store this in the visited states, and then we'll pop off the front of the queue. In our current state, we'll realize that we're at row 2, column 0, which is the goal location. So we've reached the goal, and we can return the number of steps, which is 2 steps. Okay. So now the question may be, why does this work? How would I know to add the number of eliminations as part of the row column state? Okay. So one way to think of eliminations, you can think of them as floors in a building. So if you want to think of it as a building, there's the number of rows, and then there's the number of columns. So that's how you can move on the same floor, but there's also the number of floors. Okay, so you can imagine the problem to be stated slightly differently. When you see a wall, let's say you're on floor 2, you can break a window and you can climb down a floor to get around that wall. So it's not the perfect analogy, but the idea is you can imagine that every time you go to a different floor, you're in actually a different location in space. Okay? So let's say there's a wall right here, so it's an obstacle. So you break a window, you throw a rope down, and then you jump out the window, and then you jump into the window below you, the floor below you. Okay. So you can keep doing that until you reach the ground floor and you've run out of rows that you can jump down to. And so that's kind of like saying when you have k equals 2, you use up all the floors, then you can't use any more, you can't jump down anymore, and you can't go around any more walls. Okay, so you can think of the state as the row and the column, and also the number of floors. So if you think about it in your mind as a physical location, when you're on the same row and the same column, like maybe the same room number, but you're in a different floor, then you can think of that as a different state, a different location in space. So that's why they're stored uniquely. So there's like x coordinate, y coordinate, and a z coordinate. All right, so you can think of these as coordinates in space. And that's why you can think of the number of rows and the number of columns and also number of eliminations as your state. Thanks for watching. If you'd like to see how to code this up during a live interview, please go on to the next video where I'll demonstrate how you would write this code and also talk about it during a live interview. So please go on to the next video.